So, good morning, everybody. Welcome to day 2. I think it's 9:30. We should probably get started because it's a lot to get through. I don't know if people saw the message on Slack last night about downloading data into Docker images. If you have done that, great. If you haven't, then please download the Docker image and also those data that are on this website. The website link is also posted in the Slack. So it's mostly just clicking and copy pasting into your terminal, hopefully. If you haven't done this yet, then download the Docker image and the data during the lectures, please, because this will probably take a while because the Wi-Fi isn't too great. It's probably gonna, hopefully everybody will manage to download the data because you're downloading some 30 gigabytes of data. And if this is 50 people times 30 gigabytes, you do the numbers. I don't know what the Wi-Fi is like, but please start this now. It works? Excellent. Okay, nice. Anybody else successful spinning up Casa? Because what I was saying before everybody was there, once you've downloaded the Docker image, I'd like you to go into the Docker image following the instructions on either the tutorial for the imaging or for the VLBI, it's the same. Just go into the Docker and spin up Casa. And then when you spin up Casa and you have a logger window popping up, right? So a second window where there's all the logging information. If this pops up, you're good to go. If you get sort of errors, let us know, ideally after the first lecture, and then we'll just see what we can do, all right? Just to make sure everybody has a functioning system. With that out the way, unless there's direct questions or feedback? No? Okay, good. Then I would say we can get started. And we get started on imaging. So this is actually a lecture prepared by Arpan, but Arpan couldn't make it. So it's my honor to actually give Arpan's talk. And this one will be all about how to image the radio sky, right? You might think this is trivial because, you know, if you're used to optical astronomy, you take your CCD, you get your image, bam, you're done. But that's not quite the case in radio astronomy or in particular in radio interferometry. So you saw this particular graph already yesterday. Just to remind you, we're talking about radio waves. So in the electromagnetic spectrum, we're at this end here. I mean, we're not actually talking about 10 to the 3 meters in wavelength. We're talking centimeters to meters, what we're doing here mostly. And why we're doing it is sort of also depicted here, right? So this shows you a little bit of what sort of radiation gets down to Earth, right? So the X-rays are mostly being absorbed by the atmosphere, right? So that's why we're sending X-ray satellites up into space, because down here, luckily, no X-rays come down to Earth. Then, of course, we have this very narrow window of optical light. Of course, we all know that because this is how we see our stuff. Then there is a little bit of infrared, also doesn't come down all the way through. So that's why we have things like Sophia flying around, because they need to go up to detect this sort of variation. Everything else is absorbed along the way mostly. And then we go down, of course, not all of the infrared, but some of it. And then, of course, in the radio, everything comes through. So that's why we love to do radio A. It's, well, cheapish, because we can build things on the ground. We don't need to go to space. We don't need aircraft. But, of course, some of this is also absorbed, which is why things like Armour is actually high up in the mountains, about 4,000 or 5,000 meters high, to just get above the atmosphere somewhat. Now, the very first measurement of a signal in the radio from space was actually done by Karl Jansky. You may have heard the unit Jansky. This is actually dedicated to Karl Jansky, the father of radio astronomy, as he's sometimes called. And what he had done in 1931, 32, they had built this directional antenna meant to actually detect statics, as they call it. So, he mostly found thunderstorms. But he also found something which came through his dish. Once every day, Rose came down, and the interval between the appearance of the signal was some 23 hours and 56 minutes. And he had a colleague, an astronomer, who told him, hey, this is actually a sidereal day. And it didn't take too long for Karl Jansky to figure out, hey, I'm actually seeing the galactic center, because the signal was in the direction of Sagittarius. And then in the end, he figured out, okay, we're actually looking at the galactic center, and there is radio emission from that. And the very first person who could be called the first radio astronomer was Grothe-Reber, and he built a parabolic dish, and he actually also did the first mapping of the sky. Here in Greenbank, there is this reconstruction of his dish, well, of a dish, that he used to produce an image like this. So this is an all sky map in the radio. I think this one here is around 160 megahertz. And anybody, any idea what this might be? Thank you, exactly. So this is just, the disk that we're looking into. So this is looking into the galactic plane. Now, let's get into a bit more detail. So with radio, so with actually pretty much everything in the radio, we have a limit in terms of resolution, because when you saw this map here, this was of course extremely crude, right? You can't really tell anything. There is something happening, but you have no idea what actually is happening. And this is all due to the resolution, and the resolution of a radio dish or also of the radio interferometer goes as 1.22 lambda over d. So mostly it's just the wavelength divided by the size of your dish. So just as a comparison, or just to get some scale, the human eye in the optical has a resolution of some 28 arc seconds, and the sun is 32 arc minutes in size. So obviously we can resolve the sun, right? It's not just a big blob across the sky for us. We can actually tell the sun apart from other stuff. Now, if we wanted to get a resolution of, say, 28 arc seconds in the radio, we'd need a dish of some 2.7 kilometers, and I'm actually not quite sure, should have done the numbers, what wavelength ARPAN was using here with the 2.7, but I'm assuming roughly a meter probably. So if we want to go to higher resolution, we obviously need quite a big dish. But there is a limit to how big a dish you can build. The biggest right now is FAST with 500 meters. That's not steerable at all. So you have the sky drifting past, and you can have sort of an active surface so you can see a beam a little bit, but it's not particularly practical because you have one big dish sitting there. So what we can do, what we can think about is we can actually just split up our dish into individual parts and we take it across the globe. So this is what's kind of depicted here. You have your parabolic dish, and you can split this up into individual elements, right? You have a far source in the far field. You got the radiation coming in, and in the parabolic dish, it's all being collected in the focus, and it's being summed up, and it's coherently. Now, if you want to make this bigger, well, I should actually also add here, the path lengths, of course, are such that this comes in phase in the focus, which is why it's in the focus, which is focused. So now you can, of course, think about, okay, let's just decompose our dish. We take our little tiles, we take them elsewhere, i.e. we make our dish bigger, and we just need to know where exactly we put our individual pieces of the antenna. So theoretically, we should be able, if we know the geometry, we should be able to actually compute the delay. If we take this whole thing somewhere else, then we should be able to figure out with some geometry, if we want to focus it all in one point, we can then calculate with the speed of light what we need to do to our wave to actually add it up all coherently. Now, and this is something that we do, but one step further. Why do we call these things interferometers? Well, in the end, with a double slit, what you have is that you got some plane parallel waves, say monochromatic, comes in and you get this, you have the pattern, right? You have the interference pattern on the screen. We've all done this in physics, maybe not 101, but 201. And then you have the nice interference pattern in the end. And that's the exact same thing that we're doing with radio interferometers, right? You can think of each individual dish almost like a slit if you want. And you just need to get all the delays in geometry right to have constructive interference to add things up coherently. So let's have a bit of a look at the geometry, right? So we have one dish here, we have another dish here. They are separated by a baseline length, call it B, it's a vector. Then we have what is called the phase tracking center. So both stations are looking at the exact same point in the sky. Then we have a source, which is, in general, offset from the phase tracking center. So there is a bit of an offset, call it sigma. There's a source. This source emits plane parallel waves, and the path difference. So there is this wavefront arrives at this dish first, and then there's a path difference, which is just the base length times the vector s, and s is this particular direction towards the source, and s naught is the direction to our phase tracking center. So that's the overall geometry. Now, addition number one, we're now receiving an electric field, which is nothing else than just the intensity over the extent of the source, right? So this is just the intensity distribution of the source. And then we have a phase term, which of course goes with, depends on the frequency and depends on your location where you are on Earth. The same is true for the other dish. We have the same electric field, but of course now we're in a different location, so there is a phase offset between the two, and this phase offset is mostly given by this path difference. Now what we measure, gee, there's a trailing little symbol there, never mind. What we then measure is what is called the visibilities, and the visibilities is just the complex, the cross correlation between those two individual electric fields. Now, if we go through the math a little bit further, so we start off with this, and we just insert the electric fields for the two. And we then realize that this particular factor here, right, because you do the multiplication, this particular factor here, k times r2 minus r1, is nothing but the wave number b times s, right? So the base length times s. And then we arrive already at our visibility as a function of the baseline length, which is the intensity of the source, exactly the total intensity of the source times this phase factor here, right? So this is just, if you want, if you take a particular phase, it's just a cosine or a sine wave. So it's essentially, you have the intensity times a phase factor, and this whole thing is then integrated over the extent of the source. D omega is just the extent of the source, right? You integrate over the source structure. Now let's go through a little bit of more geometry just to get where we want to get at. Because what we want to do is we want to now relate the coordinates of our antennas on the globe, of our stations, our baseline coordinates. We want to relate those to the coordinates on the sky, right? We want to somehow put our antennas and our source structure into one geometric system. So what this is then the UVW coordinates. We have U, V, and W. U typically U points towards the east, V points towards north, and W points in the direction of our source. So W is the same direction as S0 here, right? The phase tracking center. Now, then we have L, M, and N. L and M are the so-called direction cosines. They describe where the source is, they describe what the source looks like on the sky. And L and M, and also gamma, which is in the direction of the source, are just the direction cosines. Cosine alpha, cosine beta, cosine gamma. And then this whole vector S towards the source is LMN, and N is nothing else than 1 minus L squared M squared. The UVW coordinates are the baseline vectors in units of wavelength and units of lambda. Now, d omega, our integration goes over d, you just do the replacement of variables. You come up with d omega as dl dm over n, which is this particular factor here. So this is just if we talk about UVW coordinates, this is what we're talking about. We have UV, U east, V north, W in the direction of the source, and then we relate this to the direction of where we're actually looking at. And then we just do a little bit of geometry, and then we end up at the UVW coordinates. Now, with this sort of geometry in mind, we stick everything into this particular equation that we came up with before. So we stick in our S, B, and D omega, and we arrive at what is sort of the overall Franz-Bhattacharyya theorem, which, if you think of coplanar arrays, so you're thinking of that, your source is very far away. It doesn't really matter that Earth is curved because it's so far away. We can actually think of it as a coplanar array. And we're talking about a small field of view. In this particular case, we can get rid of the W term, right? Then W, because we don't care. So, the distance to the source doesn't really matter. So W, we just ignore it because it's the same for all. So we just, for small field of view coplanar arrays, we ignore the W term, and then we arrive at this Franz-Bhattacharyya theorem, which is our visibility function, which is nothing else than the intensity distribution of the source in terms of L and M, and this phase term here. And what you then also see is that the visibilities in terms of U and V is nothing else than the Fourier transform of the intensity distribution on the sky. Right, so this is for a 2-element interferometer here. Any questions at this point? Probably completely overloaded already. Okay, no questions, good. Now, like I said, so the sky intensity and visibilities are just FFT pairs. So we have our interferometer, and it actually just gives us back a Fourier transform of the sky. Ideally, we measure these Fourier coefficients of a certain scale are then defined by our baseline length, right? So different baseline length measure different parts of our source on the sky. So short baselines see the larger structure. Long baselines are only sensitive to point sources. And if we want to get our intensity distribution on the sky back, all we need to do is to do an inverse Fourier transform of our measured visibilities, and bam, we're done. Easy enough, isn't it? In real life, things are, of course, a bit more complicated. So we have our wave coming in at our antenna. Our antenna, of course, receives this, right? All comes in to our electronic system. We have low noise amplifiers because the signal is extremely low, and we just need to amplify everything to get anything. This is being down converted. Then there is a bit of filtering happening. Then there is conversion down to baseband happening, and then it's going into a correlator. So with all this complexity, which goes in there, the main point here being that it's not as simple as we have our visibilities, everything is perfect, and we just do an inverse Fourier transform. Along this way, a lot can go wrong, right? So there's a lot of calibration going in before we end up anywhere. Next question then is, for now we had a 2-element interferometer, but then, are we actually good to go with just 2 antennae? Well, the thing is, with just 2 antennae, and say, in this case, just a monochromatic wave, all we get is 2 points on this UV plane because it's all frequency dependent, right? So actually what we get is the observed visibilities that we get are the visibilities, but convolved with a selection function, right? Which is just wherever we have a point in the UV plane, this is the only information we have. So we're actually convolving the visibilities with our selection function. Now, if we were to inverse FFT this, what we would get is not the actual intensity distribution, but we get the point spread function. And the point spread function is the inverse FFT of our selection function, convolved with the actual intensity distribution. So we get something that is not quite what we want. So if we have just 2 antennae, it'll actually look something like this, right? So we have, we'll look at these a few bit more, the UV plane. So the UV plane is nothing else than the representation of your array in this particular geometry of UVW. Each baseline has a U and a V component, and 2 dishes make up 1 UV point for a monochromatic wave. And since these are real quantities, this is Hermitian, so we actually have it, it's symmetric in the UV plane. So you actually get 2 points, but it doesn't necessarily help you too much. Because what you then get with just 1 point, all you get across the sky is just a sine wave, right? Because you only have, if you go back at this particular equation here, right? So we have L and M, we have just a point source, and we have 1 U point, 1 M point, which means we have just 1 phase here. And any function with a phase is nothing than just, a sine wave, whoop, going the wrong way. It's just a sine wave across the sky. It doesn't really help you to see anything, does it? So what we then can do, we can, of course, add a 3rd dish. So now we have 1 baseline here, another baseline here, and since we have 3 dishes, which means you have 1, 2, 3, what is it, 6? No, 2 baselines. What is it? Okay, doesn't matter. We have 3 baselines. So now we have 1, 2, 3 points in our UV plane, and then we have the interference of several sine functions across the sky, and you get something like this. This is our point spread function on the sky. With a point spread function like this, you, of course, won't see very much. So what you really want to do is you want to fill in this UV plane as much as you can to get a nice and clean point spread function that gives you a nice response to a point source. So if we add 30, as Arpan has done here, you get something that reminds me a lot of a VLBI point spread function. I actually think this looks pretty good, but this is just me doing VLBI. But it's if you think of something like the UG-Marthi or the VLA, where you have lots of baselines and a nice setup, you actually get a much nicer image or a much nicer point spread function just from a snapshot. So the solution here, of course, is to either build more antennae, because what you saw here is just a snapshot, right? So it's just one integration. And why I'm saying one integration is, luckily for us, the Earth rotates, right? So at any particular point in time, we have our baseline in this coordinate system, and it gives us a UV point. But now Earth rotates, which means the relative position between antennae and source in the sky changes, i.e. we get another point in the UV plane. So this is called Earth rotation synthesis, because you just stare at the source, and nicely enough, because we're rotating, the geometry changes somewhat, we bit by bit fill in our UV plane. And then once you've done this, depending a bit on the array, but you can, I guess, up on here, use some 30 dishes, you integrate it for half an hour. So you fill in the UV plane and you get somewhat that actually looks like a proper point spread function with a point source, but you still have already here, you see what we call side lobes. So it is not a perfect, it's not a perfect point spread function where you have really just one maximum. It is a bit messy, but that's just the way it goes in interferometry. Now, so if you observe long enough and the Earth rotates, you get a nice point spread function. And what you need to remember here is that you just want to integrate, of course, as long as you can, but typically 6 hours is enough, because 6 hours gives you the same, because as I was saying earlier, visibilities are real. It's a complex quantity, but the visibilities are real, which means it's Hermitian. So you actually get, it's symmetric, so you get 2 points for each integration. So with 6 hours, you actually pretty much fill in your UV plane. If you observe longer, you're not going to gain much. So are we done here? Not quite, because we need to invert our visibilities, right? We need to go for an inverse FFT. Like I said earlier, we need to deconvolve our point spread function also from the actual intensity distribution. How do you want to do this? Well, there is now, you can of course go for a direct Fourier transform. Direct Fourier transform extremely slow, expensive, and that's just not feasible because we got loads and loads of points. So we want to go for a fast Fourier transform. In order to be able to do a fast Fourier transform, we need a regular grid. That's the assumption behind a fast Fourier transform algorithm, that you need to have a nice regular grid. If you look at this or at that, that is anything but nice and regular distributed, is it? That's why we need to come up with something smart, which means we're gridding and we're weighting our visibilities, right? So we take our visibility or our UV plane, and we first of all split it up in a regular grid. But of course, on this regular grid, depending on where you are in the UV plane, you will have more or fewer points, right? So when, just to emphasize this point, so here this is already somewhat of a regular grid. And if you look in this particular part of the UV plane here, you have what, 1, 2, 3, 4, 5, 6 points. And in this particular part, you have many more points. So this is then where the weighting comes in. And the weighting is such that you have your grid, and each of these grid cells, or in particular, each of these visibilities, gets a weight. And there's two extremes. One is called natural weighting. In natural weighting, what you do is that each particular grid cell has a weight, regardless of how many points are in there. And then there is uniform weighting, where each visibility gets a weight. So in the one case, where each grid point, regardless how many points are in there, gets the weight, it's called natural, and this emphasizes the short baselines because it gives more weight to all those short baselines, because it downweights the long baselines, where there's only 1 point, you have, of course, less weight. And in this way, you can sort of steer your beam. You can, with natural weights, you have higher sensitivity, but less resolution because you're emphasizing the short baselines. With uniform weights, you're emphasizing the long baselines, so you get higher resolution, but your point spread function is going to look pretty crappy because you have all sorts of holes in your UV plane. So we gridded, we weighted, and then we deconvolve the whole thing. So we have to get rid of our, we now have a point spread function that hopefully looks kind of nice, but we of course want to deconvolve the point spread function and the intensity distribution because we want to get our actual image back. So the question is, how do we actually do this? And this is something was developed by Högbohm, and it's called the clean algorithm. So what we do in the clean algorithm is that we take our visibilities as we have them, we do our Fourier transform of this entire point spread function of our all available visibilities, and we get what is called the dirty beam. In this dirty beam, we're going to have a brightest pixel. What we're going to do is we're going to take the value of this brightest pixel, we're going to take it where it is in the image, and we're just going to scale it by a factor of 10. Well, we're actually just going to take 10% of that value, scaling by 10. So we're actually downscaling, what's the right term? So you take 0.1, it's called the gain factor. So you don't take the entire intensity of this peak, you take 10% of that. You take this as a component, you convolve it with your point spread function, and you subtract it from the original, and you get then what is called the original. So it's an iterative process. You sort of say, okay, here's my brightest point, there's a point source. Now, I convolve it with my point spread function. What is it going to look like? But I'm only going to take 10%, and this I'm going to subtract from the original, and then I'm going to go back, right? I'm going to store this. Okay, here's a component. This is what I have. I'm going to subtract it. I go back, and I go back to this partially cleaned image. I do the same thing again. I look, what's the brightest part, and I'm going to subtract the point spread function convolved with this model again, until in the end, I have subtracted the point spread function from all the components in the image, and I have hopefully something in the end that is Gaussian noise, a Gaussian noise residual. You're never going to get a Gaussian noise residual in interferometry. It's never going to be Gaussian because the point spread function is just crappy. But with a nicely filled UV plane, you can get that. Did I miss anything from this slide? I don't think so. I pretty much all I said here. So just to sort of, this was just the text version. Now let's go through this. So we have, in the beginning, we have our data. Then we have our model, which is, our point source and the point spread function. We subtract this, we have a residual, and we go back. So this is what's happening. We're going to do this later on in the imaging and also in the other session. There is what's called the minor and the major and the minor cycle. So the major cycle is that we do the FFTing, we find the components, we subtract it. This is one major cycle, and the minor cycle is always the part where we look for the components, we convolve it, and we just save this model of components that we have, convolved with the point spread function, but only 10% of the flux. Before I move on, as I'm almost done with this part, are there directly any questions to cleaning? Probably way too much to absorb, but yes, go ahead. When do you stop cleaning? Yes, when do you stop cleaning? That is a very good question. When do you stop cleaning? So you can either, you set yourself a criteria, right? So you can either say, okay, I want to stop cleaning when the brightest pixel in my residual image is only, say, 5 sigma of the RMS in the residual, right? This is one way to do it. Typically, that can take forever. It depends a little bit on your data. If you do with that, the other alternative is that you just go by a certain number of iterations. That you say, okay, once I have, say, 100 clean components, we're done. Then we stop. Right. So it's either so that's the most typical things. Either a noise-based criterion, or you say, this is just a point. If you really know that you only have a point source in your image, it's actually wiser to go just with, say, 100 iterations, because you're not going to get anything else out anyway. So that's when you stop. Okay. Anything else right away? No? Good. Now, so we've gone through all this drama of our point spread functions and of degridding and of deconvolving, and then you may ask, okay, but is it actually worth it? Because, you know, isn't that kind of good enough? Because, you know, that's the galactic plane, awesome. But no, it's not good enough, because this is, I think, one of the most cited images of the galactic plane. This is from MACAT. I think it was the very first data release, because this is really, I don't know if you've seen MACAT. It's one of the SKA precursors. It stands on the SK site in South Africa. And you have, you know, these massive structures that you can nowadays resolve on the galactic plane. You got these massive bubbles, and you have all sorts of arcs and filaments and whatnot. So in conclusion, for this first part, yeah, radio astronomy contributes to all parts of astrophysics. It's a tedious process, but once you mastered it, you can do all sorts of nice things, from star formation, black holes, AGN jets, pulsars, transients that we'll get to later on. You can do molecular gas, EOR, gravitational wave detection, all sorts of things. And, you know, from starting off with Karl Jansky, now we're at, I think this is still spectacular. I like looking at it. Okay. And that will be the first part on just the quick intro to imaging. Any further questions right at this point? Yes. Yep.
Yeah, that model image, where did you get? You prepared before you started cleaning, or how did you get that model image? Deconvolution part.
So before you started, well, the thing is, I probably confused you.
From the residual image to the model image.
From the residual image to the model image? Well, so you know what? This plot always confuses me too, to be honest. So, you know, it's okay that you get confused. So to start off with, right? So forget about the model and the residual in the beginning. You start off with your data, you grid it, you Fourier transform it, and you get, I still find this confusing. You get your dirty image, right? And then you take your clean components out, and you have a bunch of clean components, and then you convolve this with a Gaussian, and you have a model image, right? Something, you have your ideal image that you'd get with these clean components. Now you convolve this with your point spread function, and you do the FFT back, and then you're back to your data, but from the first model. So you get 10% of those peaks, convolved with the point spread function, degridded, and this is sort of what the visibilities would look like if you had just these few components in that. That is the model image then, which you then here subtract from the data. And then you have a new residual. You have a new, sort of the residual is then your new data. You start from the residual one, and then you just do the whole process again. I don't know if this made sense.
Okay.
Other questions?
Any other questions at this point? Okay. No. Okay. And I'm just going to have a quick drink of water, and then we'll continue with the next bit.
Yeah, so I think then Franz will go on the VLBI part. So either you can hold your questions for the VLBI part to end, and then come up with the, this is also imaging. Now we are just kind of going finer in the angular scales when you're increasing the baseline length. So, but the tricks which you are doing here is actually be there also. So yeah, so whatever you feel, because the hands-on which is going to come after that, you are going to do all things in the processing the data. So it's better to kind of clear your doubts now.
So I have a question. So yeah, hi. So since you have unevenly sampled data, you would grid the UV plane into using some gridding function, right? So you would essentially make the unevenly sampled data via gridding and interpolation. So how sensitive the image statistics, noise, or structures are to those functions, like interpolation functions and those?
You do get differences. So there's different gridding kernels, different strategies for the gridding. So I haven't really played with the gridding too much myself, because I do VLBI, I do point sources, so it doesn't really make a big difference. But the weight to grid and the weight to weight does have an impact on if you have extended emission in your image, right? If you really have an array that has a lot of long and short base and you have extended emission, then you really need to be careful how you grid, how you taper, and how you assign your weights. There's a lot of influence on what the final image is going to look like. So there, it's a bit of trial and error. So this is what you, if you do interferometry, this is what you get a lot. That a lot is trial and error, what you get out. What does the noise look like? So you do need to be careful there.
Any other comments or doubts?
Just a quick intermediate question. Did everybody succeed downloading at least the Docker image? Did anybody not succeed to download the Docker image yet? I take it that everybody has the Docker image. All right. Did anybody succeed downloading the VLBI data? Looks like no. Oh yes, somebody did. Okay. Who did not yet download the VLBI data? All right. Is the download running? Excellent. What sort of data rate is it running at? 100 kb per second or a bit more? 35 kb per second. All right. Well, we're starting the VLBI session at 2:30. Maybe we'll manage by then. Leave your laptops running during lunchtime, please.
So put your power plug in, and so it's make it live.
It's actually not that much data, but depending on the connection, it can be a lot of data. All right. Good.
Somebody downloaded through USB, you can locally share the data.
If people are happy to stick whatever USB stick into their laptops, that's definitely an option, yes. So
yeah, they're happy to plug in.
Yeah, I mean, so those people who have managed to download the VLBI data, maybe we could try and share those data across with a hopefully clean USB stick or external drive. Yeah, well, if people are on Linux boxes, they should be fine. But I'll leave this to you guys. So people who has downloaded the VLBI data? Hands up. 1, 2, 3. 3. Oh, well, that's more than nothing. So if we could get 2, 3 USB sticks that go around, because it's just the VLBI data are, I think, 10, 12 gigs of data. So that should be pretty quick to actually share through USB sticks or similar. I'll leave this up to you, but maybe we'll do this during the lunch break or whatever, or just let the download running. I don't know. Whatever is easiest. If we have enough USB sticks or external drives to do this, that would be good.
Yeah. So yeah, maybe I suggest you to start doing things using the 2 disks while the down. So you start copying using the USB because there are 3 people where they have downloaded the VLBI data, and there may be
closer.
There may be 2 and 3 USB disks. So I just suggest you start while the download is happening, you start copying locally using the USB disk, so that at least you will have a backup plan ready if the download fails. So I think you just coordinate so some of you will come and give the USB disks. Through that, it will be getting circulated internally. But keep the download happens because we don't know which one will be running faster. Yeah.